thanks a lot for inviting. So this talk will be based on, well, one paper on the on the fuzzy hemisphere, that is this one, but also some old material. And I should also note that on the same day with my paper, there was a paper by Zhou and Zhou on also on the numerics and fuzzy hemisphere. So since this audience has a lot of people that experts in numerics, and this for me is like the first project that involves numerics, I was a bit worried that it will be too boring, so I decided to divide the talk roughly in two parts, which are very loosely connected. The first part is some formal story, which I mean, it's connected to the story, but to the subject, but might not have immediate applications. But I find it beautiful, and maybe it will someone will find it inspiring. And then the second half will be about the actual fuzzy hemisphere. So the plan of the talk is I start with this formal story about the quantization by the lowest Landau level projection and in relation to some mathematical work known as Berezin-Toeplitz quantization, which I would be actually curious to know if anyone ever heard about it. Oh, OK. One person. That's awesome. But yeah, people who study aspects of quantization, they usually focus on geometric quantization, quantization by branes, which is more popular nowadays, but usually they are not aware of this approach. Anyways, it's like basically formalization or making rigorous the lowest Landau level projection. And then I will switch to the hemisphere, fuzzy hemisphere, and the study of boundary criticality and 3D Ising. OK, so so just to recall, just to remind you, what do we mean by quantization? Given a symplectic manifold, which is a phase space of some classical mechanical system with symplectic structure omega, and perhaps Hamiltonian as well, H, we would like to produce quantum system whose classical limit is this Hamiltonian system. And in the more sort of standard approach of geometric quantization, well, we also assume that symplectic form over 2π is the integer cohomology class, and then we pick a pre-quantization line bundle on M, which is a line bundle with connection whose curvature is omega. And then we start to like think of what would be the Hilbert space of the system. Just taking sections of this bundle is not the right choice because it's too big. It's like saying that wave functions would depend on both positions and momenta. But then the right way to do is by that is standard in geometric quantization is to choose some polarization, which is like choosing which directions we call momenta, and then declaring that wave functions only depend on positions or independent on momenta. Right? Now, a slightly less known but alternative approach would be to actually take the same space of sections of this bundle and perform projection onto a certain subspace, let's call it H, which will be the analog of lowest Landau level in this general setting. And how do we do that? Well, and then define the quantization by so-called Toeplitz operators, where for a function on your symplectic manifold f, you replace it. You just enclose it with the projection operators onto this generalized lowest Landau level. Yes?
Does this word connote something related to Toeplitz matrix? The function of the difference of the indices?
I'm not sure. I mean, I think people also study Toeplitz operators like outside of this context. And
it's a different thing.
No, I think it involves this taking projections onto the subspace. But I'm not 100% sure. So. Maybe not the same thing. Yeah.
Can you explain, perhaps, for non-experts, why do you need to do all this complicated stuff? Why can't you just write down the Hamiltonian and some L2 space and so on and just work with this? Like Dirac and...
Well, for general M, you cannot do that. For simple...
Does it mean that you cannot do it?
Because
you cannot do what? You can construct some Hamiltonian, write down some L2 space. Why would you not be happy with such a construction?
Well, you didn't give me construction, but I assume that
Well,
just forget about this whole symplectic stuff. Just try to consider M as a.
Yes. Which M?
Yeah. What is the correspondence of this M, the usual quantum mechanics? Where
The phase space, I told you, the phase space, you know? P and Q. But in more generally, it's like some curved manifold where you cannot just simply separate and tell P's and Q's and say that wave function is just a square rootable function of Q's. Even on the sphere, actually, there, of course, you can do holomorphic quantization, but
why should I consider, quantum mechanics is more general than classical mechanics. Why should I look for a quantum system which has a certain classical limit? Wouldn't it be more correct to say, let's just consider all possible quantum systems?
Sure. Yeah, I mean, that's first of all, that's a correct question, but also you have to be all-powerful, almighty to be able to consider all possible quantum systems and then just study classical limit. That's like conceptually the very right thing to do, but historically.
Why should I consider classical limit?
Good question. Let's talk about it. I mean, it's a really good question.
No, but I think it's still a useful question. Like, what is the point of all this? So if you give me a manifold and I have a Lagrangian and it's quadratic in derivatives, I know how to solve the equations of motion and write down the modes and quantize in that sense.
Sure.
So that must not be sufficient for what you're trying to do. Why not?
Yeah, because if you're thinking about the second order system, in which case your manifold is the configuration space, and in that case quantization is a very simple procedure. But when it's like you think of it as a first order system, meaning that it's a phase space, you might run into various.
You're talking. Are you worried about things like Dirac constraints?
Oh, sure. I mean, sure. That's one way to think of it. Yeah.
But I mean, we also know how to handle that without importing all of this formalism.
Not in general. I mean, yes, we know thanks to this formalism, but yeah.
Are you going to do an example where you need it, or are you just going to do the lowest lambda levels?
I think I gave, in the introduction, I gave my motivation. So there's this formal story, but then I will give an example, and then I will switch to, okay. Anyways. Yeah, so in this case, the quantization is done by dressing function with these projectors. And then it hasn't actually been proven. There's some extensive mathematical literature on this subject, which, again, is somewhat not widely known. And one can prove that these operators satisfy, for example, the property that the product of T of F and T of G gives you the product of F star G, where F star G is like the usual star product. Well, a star product, meaning that it's a deformation of the product of functions. Now, I want to give some a physical derivation of sort of this approach that leads to two versions of this so-called Berezin-Toeplitz quantization. And namely, if you start thinking about your system in the path integral approach, in which case we just say that, well, there's some, let's say locally, or some potential alpha such that the symplectic form is z of alpha, and then we write the usual phase space path integral. Well, it is actually notoriously subtle to define. And those who have ever tried would know, but otherwise, trust me. And so one way to improve it is actually add a term that is second order in derivatives.
So sorry, my big last. H depends on just x, or also? Yeah,
well, x here includes both positions and momenta. Oh, it's like yeah. Mm-hmm. So you could sort of regularize this by high order derivatives, so make your system the second order by adding this mass term. It's like it looks like a particle of mass 2 mu moving on your space M. So now instead of thinking of M as a phase space of the system, you sort of start thinking of it as a configuration space of this auxiliary system. And what was a pre-quantization line bundle before, where like the wave functions would be taking values, now it becomes literally the gauge bundle. I mean, where the gauge associated to gauge field, and you think of, and the symplectic form omega becomes the magnetic field. You think of it as a magnetic field on M. And then if you take back the mu to 0 limit, it implements this sort of lowest Landau level projection. More precisely, well, the Hamiltonian of such auxiliary system has this form where, well, the second term is the Hamiltonian of your original system, and the first term is the some kind of operator. And it turns out that one can actually prove that you can find these quantum corrections, adjust them in such a way that this operator has large enough kernel to accommodate your quantization. So this kernel actually is, well, sort of the generalizational lowest Landau level in this case. And I told you that there are two versions of this Beres-Interpol's quantization. A second one can be formulated if you try to write a slightly nicer measure on your whatever, try to come up with a nicer measure in the path integral, where you use the symplectic volume of the Liouville measure on the phase space. So you use symplectic volume, which is just the omega to the maximal power, and then let's include auxiliary fermions.
Now M is even dimensional.
Yeah, M yeah was always even dimensional here. Yeah. Auxiliary fermions and exponent sort of write it in this form where now you have omega in the exponential, or like just a different way to write it. Then we sort of define this measure of the path integral by adding these additional degrees of additional fermions, sort of auxiliary fermions for now, and with this term in the exponential. If I consider this path integral with the 0 Hamiltonian for a second, then it actually has a supersymmetry, which was noticed a long time ago by Morozov, Niemi, and Paolo, a symmetry between these x's and psi. So in this sense, like every quantum mechanical system secretly has this hidden supersymmetry. Well, if you turn off the Hamiltonian, at least. Yeah.
If you turn off the Hamiltonian, everything.
Now I can do the same trick of adding this mass term and sort of making M to from phase space to the configuration space of the system, but with now including the fermions and while preserving supersymmetry. And there's actually a unique way to do this. Now I included, so this was the original term that I added 2 slides ago, and this is now the new term that involves fermions. And this turns out to be just a superparticle moving on M. And this auxiliary fermion became dynamical now. Now if I take back the mu to 0 limit to recover the original system, the Hamiltonian takes this form, where the same form as before, but now L is actually the square of the supercharge, and the supercharge has the meaning of the Dirac operator on M.
So you don't have the Hamiltonian yet? You're restoring the
Yeah, I restored the Hamiltonian here, right. A Hamiltonian, so it would be softly breaking supersymmetry, sort of. Yeah. And this is the Dirac operator, well, simply because the canonical commutational relations for these fermions are like the relations on gamma matrices. And then if I take the mu to 0 limit, it will be projection on the kernel of this Dirac operator. So this is sometimes referred to as the spin C quantization, or spin C Beres-Interpol's quantization in this literature. Now, since this size, they generate a Clifford algebra, so on, it means that basically the Hilbert space is the representation of Clifford algebra. So the Hilbert space are really spinners on your M, or wave functions of a superparticle, they're complex spinors on M, or like you can think of one particle states of some spinor field on M cross R. And then physical Hilbert space is the kernel of this. Well, there's some technicality. There's actually a spin C Dirac operator, but kernel of this Dirac operator, or it's a. You can view it as supersymmetric ground states of this superparticle on M. They sort of implement quantization. It's something that it was actually never published, but I worked on
a long time ago.
If they are complex spinners, shouldn't be there a dagger on the anti-commutation relation?
No, there's no dagger.
Okay, but they are not Majoranas, you say?
They're not Majoranas, yeah. So, anyways, so now let me consider an example of when I'm quantizing a sphere. This is one example where you cannot just pick P and Q. You have to use one of the sort of more general approaches in the standard. And in this language, it would mean that I take S2 with the symplectic form that n times the volume form, where n is this magnetic flux. And then the pre-quantization line bundle is a certain line bundle on the sphere, which would be known as ON. And then I look at the...
What's the n? Just number of flux?
Yeah, just number of fluxes. Yeah. So it's coefficient here.
And where is, what is position, what is momentum? Or?
Oh, I mean, you cannot split it globally, right? Because
if you could, your tension space of the sphere would be trivial. Tension model would be trivial. So it's
so physically, is this Landau level already after projection, or how should I think about it?
Oh, I'm just so after projection, I would get the. So there are like three ways to describe it. In the standard geometric quantization, that would be you're working in holomorphic polarization, where I think, say, of Z as positions and Z bar as momenta. And then I define the space of the Hilbert space here as a space of holomorphic sections of this line bundle. And in this sort of bosonic Berezin-Topos that I told you earlier, which is like just a standard projection on the Landau level, on the zeros, on the lowest Landau level, it's well, I just write it like this because this is actually the appropriate Laplace operator. And in this fermionic Berezin-Topos, so where I sort of look at the ground states of the superparticle on M, I think of it as a kernel of the Dirac operator, which on Kähler manifolds such as S2, it takes the form of this this del bar, which the Dolbeau operator, and then it's plus its dual. But in any case, this space is always the C to the power n plus 1, right? And n was just the number of fluxes, that positive integer that I fixed.
Yeah. So
are these fermions so-called Kähler-Dirac fermions? They have a whole Clifford algebra.
They have a.
They represent the whole Clifford.
They represent the whole Clifford algebra. I've never heard of the term Kähler-Dirac, but oh, sure. Now, let's think of this sphere of CP1 as in the Hopf vibration as a quotient of S3 by U1, where S3 I am embedding into C2 as follows. So there are two complex variables, Z0 and Z1. And then algebraic functions on CP1 there, after this embedding, then can be just written as polynomials in Z0, Z1, Z0 bar, and Z1 bar, such that the total power of Z's and Z bars are equal. So that it is consistent with, it respects this quotient by U1. Then, and then the basis of holomorphic sections here, it's just such homogeneous polynomials of degree n. And these are the monopole sphere harmonics, or the fuzzy orbitals, or whatever they can be called. So they are like they're not really functions. They are sections of this line bundle on the sphere, holomorphic sections. And then these functions, actual functions on the sphere, after quantization, let's say in any of these approaches, I can represent them. I can just simply replace z bars by appropriate derivatives over z, and then they become sort of this n+1 by n+1 matrices, which can be, I can think of them as such differential operators, for example, acting on the space spanned by the homogeneous polynomials of degree n in z0 and z1. Anyway, but this is just a sort of more the standard thing that all you know, but in the maybe more algebra geometric language. Huh?
These matrices, n+1 times n+1 matrices.
The fuzzy spherical harmonics, you mean the ones that are that form a basis in the limit, or the ones that, or the monopole harmonics?
Which one?
In the non-commute field theory on fuzzy sphere, they use this so-called fuzzy spherical harmonics to construct.
So you mean the ones that in the limit of infinite flux will give you actual basis?
No.
Well, I mean, it must be then. I mean, if you're not talking about monopole sphere harmonics, then it must be these, right? The ones that are actual functions on the sphere. And if I use this, if I use this embedding and parameterize z0 and z1 as in sort of the standard way, then this fuzzy harmonics, whatever, the monopole harmonics, they take the known form, the well-known form, and each of these, they're sort of localized at a certain angle where this function takes the maximum value. Now, as I said, these functions after quantization, they form this closed algebra of n+1 by n+1 matrices, which is consistent with SO3 invariance, which is one of the best things about the fuzzy sphere, of course. And the size of the matrix plays the role of the UV cutoff. Now, just a side remark that also this model of fuzzy sphere is also fantastic to a model for studying the classical limit of quantum mechanics, so, which is a whole topic of separate discussion. I mean, of course, one could ask why it's important to study classical limit, and such questions and the questions of decoherence, they can actually be studied closely within the fuzzy sphere, just completely independent of using it as a UV regulator.
Can I ask a question about it before you go to that second half of the talk? So you showed us that you have this very powerful machinery that you clearly master and better than any of us, and you can recover using this machinery other, elegantly results that people recover using other ways. Like, you, for example, by really physically putting magnetic field, working out wave functions, you recover the same quantum mechanical system, right, using your machinery. The final quantum mechanical system is exactly the same, but just recovered in a different way.
Sure.
So is it just a matter of elegance, or is your way of recovering it gives you some extra insight into the system that other approaches miss? What is the point of this? Can you advertise a little bit? Why should we think about it this way? Why should we learn this BT? Because if in the end we just want to do fuzzy sphere, do we have to learn this?
Well, as I said earlier, it doesn't necessarily apply immediately, have like immediate applications. So you don't have. Not clear. Yeah, but it might inspire some ideas.
Is there some way of thinking? I mean, here you have an even manifold, but say you wanted to do something on S3.
Yeah. Right. So
does it help you maybe come up with the right ideas for S3?
No, and because here you start with a symplectic manifold, it's even dimensional. Yeah, you have to add something. I mean, in case of S3, I think there are some approaches in the literature, or right for S3. But my best idea would be to actually quantize the base, this S2, and then somehow truncate the fibers of Hopf fibration.
But when you when you do calculations using this formalism, I mean, the fact that this quantum mechanical system can be recovered using this formalism, does it lead to any advantages, computational advantages? What are the advantages here?
Well, advantages is that certain people like to think in this language.
But why do they like to think in this language?
Personal preference. And
it's not a criticism. I mean, I see that there are lots of people who do this. I would like to understand why. Maybe then I will also learn.
I mean, I could ask the same question: why you prefer doing the other way? I mean, it's.
I don't prefer. I just see that some people do some calculations, they get a concrete result, and if the goal is just to get a number in the end. You can say, okay, if there is a formalism, this formalism is going to get you faster to the number. That's also a reason. Formulas are shorter or something like that. I don't know. Can you please start like that?
This formalism.
It's easier to remember the multiple harmonics.
Yeah.
Okay. Oh, thank you. Yeah.
Sorry, why?
It's just Z0
Z
and
to
K.
some power.
That's the same in the fuzzy sphere. They were already written down in spinner.
Yes.
It's the same exact. They're just given different names, but
They were
called U and V. Yeah.
Yeah.
No, it was the same. They were called U and V and was the same function.
It's just like in a bootstrap. It's not CHU.
What's the reason why people are excited about it?
You mentioned supersymmetry in this format again in the same way. Does this, like, I guess in the case we have Hamiltonians just standard first order systems, this shows that more or less all of these systems are integrable or something like this, but when you add the Hamiltonian, is there any use to the approximate supersymmetry that you can interpret integral?
Not that I'm aware of. I don't know if
Okay.
it's never been used.
Fair, thanks.
Yes?
Question. And so would this formalism be more effective when you are fuzzifying other manifolds?
Well, at least it gives you a conceptual sort of clear way how to fuzzify other manifolds. Yeah. Well, symplectic manifolds. It's a bit unclear, like with those that are not symplectic. Like there are some still proposals in the literature how to fuzzify. Like I've seen. Well, anyways, it's a separate discussion. But for symplectic manifolds, it's like just tells you how to work with it. Yeah, how to fuzzify. Anyways, now let me look at the hemisphere. Sort of thinking in the algebraic way to how do I pass from a sphere to hemisphere? I just consider functions that are invariant under reflection with respect to the equator. In this case, reflection in terms of these variables looks just like this. And so if I look at these functions, then this invariance under reflection simply means some symmetry of these coefficients. And if I write these coefficients as an n by n matrix, it means that it's just symmetric with respect to such sort of taken transpose, but with respect to the wrong diagonal. And such matrices, they actually do not close, do not form an algebra. But if you might consider a further truncation where you throw away these corners, and they sort of correspond to overlaps of these fuzzy orbitals on the north and south hemisphere. So they, in the large n limit, they become suppressed. Anyways.
So this is fuzzy RP1, is that right?
No, it's. I'm looking hemisphere, fuzzy hemisphere. I want to. I'm not. No, I'm not identifying antipodal. I just doing reflection with respect to the equator. So once I look at it in this way, then it basically means that I simply throw away all these harmonics that are localized in one of the hemispheres, and then keep the other ones. And yes.
So we know that let's say you have this Landau level, right? And we know that on an open manifold, Landau levels have edge states. So somehow this corresponds to gapping out the edge states, and that requires some non-local perturbation on the boundary. The-
I guess, but
I'm just saying that suppose you started with just particle on a sphere
right.
In magnetic field, and you don't truncate the lowest Landau level, right? So you got Landau levels, and they're flat. But now suppose you put on, I don't know, infinite potential on the lower hemisphere,
right.
so the particles cannot go there. Then you don't actually get flat Landau levels, right? You get they're flat in some region, basically corresponding to inside of the upper hemisphere, and then as you get close to the edge, you get the edge states that that go up, right? And somehow this approach seems to get rid of those edge states. And
because I first, so I guess because I first project to low Landau level and then cut.
But why should we do, Max, what you want to do?
Because you want to keep locality.
No,
I think this approach somehow adds a non-local perturbation on the edge, which might be okay because maybe this non-local perturbation only affects charge degrees of freedom and acts as a irrelevant perturbation to the CFT. But I think this is something that should be thought through.
Okay, maybe we can talk about that. Thanks. Anyways, any more questions? Or comments?
So these orbitals, so you keep these orbitals. Before, when you had full set of orbitals, you could pick any point on the sphere, and you can, considering some appropriate linear combination, you could construct a state which was approximately localized near that point.
Right.
So now you keep these orbitals which are only inside the hemisphere. Is it still true? Do you think it's still true that by taking linear combinations of these ones, you can still construct for any point inside that hemisphere a state which is approximately local near that point?
If it's far enough from the equator, then yeah.
Okay.
Okay, now I want to do the. I want to put some degrees of freedom on this hemisphere, and I actually will consider this Ising-like model from the foundational paper of this field, where of course, I mean, the model in the universality class of Ising model that flows to 3D Ising CFT. Well, okay, so that's the standard story that all of you know, so I can probably skip over it, so that where we have this spin up and or isospin up and isospin down electrons, because it's not a real spin, as it doesn't contribute to the angular momentum and doesn't couple to the external magnetic field, but magnetic flux. But it couples, of course, to its transverse magnetic field in the Hamiltonian. So okay, I will skip to save some time because you all know this. Just to emphasize though that so we have n here, n orbitals on the full sphere. We had n orbitals, so there are 2 n available slots, and we consider the half-filled space where n electrons, where these fermions are added to the sphere. Now, okay, it's again just a review of that model that you all know, with the Hamiltonian written in terms of the this spinor bilinears, or in the components. So now, what I wanted to emphasize though is that so we know that these symmetries include the full rotations, which is the great advantage of the fuzzy sphere. The Ising, which just flips the spin, and well, here we have to include minus because we have to, after we flip them, we have to commute, so there's an extra minus. and particle hole symmetry, which according to which maps the subspace with k electrons into subspace with 2n minus k electrons, but it preserves this half-filled subspace. And in fact, this particle hole symmetry only commutes with the Hamiltonian when we're restricted to the half-filled subspace, right? And the symmetries are very useful because the more symmetries we preserve, the less finite size effects generally we expect to have. Now, in the original work, there was the order parameter that was used to diagnose the criticality, and so they had this. They studied the dependence of the order parameter, plotted it against the transverse magnetic field for different values of n, and divided it by the expected scaling that expected at the conformal point, and then got this plot, right? And then we want to do something also similar on the hemisphere, but with the boundary order parameter, which will be okay. There's also this another little thing that I will mention, but I wonder what maybe people have any comments about it. If we replace the Hamiltonian by, say, shifted by some function of L squared, where L squared is the square of the angular momentum, the energy spectrum will obviously shift, and like won't look conformal the way it looks, say, without the shift. But at the same time, the eigenvectors will not change, including the vacuum, at least let's say if A is positive. So if we just look at the, so it means that this plot will also look the same. But the spectrum will sort of shift and will not look conformal. It means that when we do this analysis, after identifying the critical point, we might need to also shift the Hamiltonian by some conserved charges to sort of make the spectrum look more conformal.
But L squared is non-local. It's a non-local operator in real space, so you should not add non-local terms to your Hamiltonian, right? Otherwise, you may not end up with the local CFT.
Okay.
But it shouldn't matter for the reason you said, right? It's you can diagonalize L and H simultaneously, and that's just going to shift everything by L squared.
Well,
if you're just trying to find the spectrum.
Yeah, but what does it mean it doesn't matter? But it changes the spectrum, and the spectrum is an observable that you're trying to extract. So
the right spectrum is the one with the local
Yeah.
Okay.
And
So
you could take A large, and then that would be a dream if you could compute that.
You can project onto this.
Yeah, then you could project that to a useful subspace.
Otherwise, I mean, why do you change by L squared and not by hyperbolic tangent of L squared?
Well, yeah,
or, any function or just by a function of H as well, right? Why don't consider sine of H?
Sure. Yeah. So
makes no sense.
But if you start with a random whatever Hamiltonian you write and then try to, so I guess so the idea is that the local Hamiltonian should be the right one, right? However, when I perhaps it's related to your comment, because when I work on the hemisphere, I had to sometimes perform such shifts to improve the result. So perhaps there is this some non-local contribution along the boundary, which is because I did this truncation in this way. Okay, so now when we're on the hemisphere, of course the rotational symmetry is broken to U1. Oh.
So the previous comment was already for the fuzzy sphere. You don't mean the hemisphere.
Yes, it was a comment about the sphere, but then it's not necessary on the sphere. Like if you take the Hamiltonian that
written in the original paper, yeah.
And this on sphere, I don't think one is allowed to do that.
Right.
Okay. But why? I don't understand. Is why if H and R squared commute, what was the problem? I understand it's non-local, but they both commute.
But you change the spectrum, right?
I thought it was just a. Why are you doing it? Why are you shifting it?
Oh, so here I'm just saying that you could do that, and it could happen that if you wrote some Hamiltonian, that it would actually not be the one that corresponds to, that gives you right conformal spectrum, but it could be that it differs from the right Hamiltonian by such shift.
If you had a local theory, that would never.
The whole point of the construction of the original paper was to choose a Hamiltonian. They didn't choose an arbitrary Hamiltonian. They chose they could be gazillions of spherically of rotation invariant Hamiltonians that one can choose. They chose a very good one, which was guaranteed by the construction that is going to tend to local CFT in the limit. It was guaranteed. It was not an accident.
But I'm sure there was a lot of work in the background to choose the right Hamiltonian.
If you start doing these shifts, then you basically annul all their careful choice.
Not so much work. It's the Lagrangians manifest their local from the outside.
Yeah. So we should be careful. When you say we could do this, then can is I'm not sure it's the right verb here. It's not the right modal verb.
I mean, presumably you're doing this because you got some answer and you found that adding this improved it or something. Is that?
Well, that would be on the hemisphere. But as I said, the purpose of this slide is to hear comments.
You may contemplate doing it for a second, but then immediately realize that that's not a good idea.
Yeah, otherwise you just add any function on L squared and you can manipulate, make your data whatever you want.
I don't know if you have an idea.
In principle,
Can you use this to project onto the system?
It depends if you consider that the CFT is a property of the state or a property of the spectrum. And it also depends a bit on what are the objects in your CFT. If you start having anionic, for example, objects in your CFT, you might need to do non-local transformation to recover something that makes sense in the local language. Like in 1+1D, I have examples where if you work in the natural language, in terms of the CFT, your local operators are non-local and vice versa. So for Ising, it's a bit irrelevant. Locality is not a trivial question.
No, it's just a technical. It's a technical.
Yeah, but still, the whole thing.
But you say you have evidence that on Hemisphere one actually needs to do that.
Well, one needs to do this to improve the results. So,
with R square or LZ? You use R square or LZ on games?
Well, LZ because yeah, on the. Well, here I said L squared because I'm like sort of talking about full sphere on the slide, and L squared is the only one that would not, like, adding it to the Hamiltonian would not break any conserved charges. But on the hemisphere, you're allowed to add LZ without breaking, well, LZ or LZ squared, depending on whether you keep.
LZ squared is not.
LZ squared is not okay, it's not local, but LZ is local.
Yeah, LZ. But LZ doesn't commute with P.
Oh, LZ is now bounded. Is that your point?
No,
I would never add LZ because that's not bounded.
Yeah, now you don't have the negative ones.
Yeah.
And it also violates if you choose a scheme where you preserve this particle hole symmetry, then adding LZ violates particle hole symmetry. So
I mean, it seems to me that you are not doing justice to locality by kind of chopping off the lower hemisphere too brutally.
Right.
That's related to Max's comment. So maybe if you can repair that, you wouldn't need all these kind of things.
Maybe we can let's look at the results without improvement and with improvement, and then maybe we can give better input, because right now we are a little bit in the dark.
Well, Slava, you shouldn't expect to see what you want to see, though. You know? No, because I couldn't anticipate all the questions. So. Anyways, well, yeah. Let's see what there is there in the rest of the slides. Yeah.
Okay. Let's.
So the symmetries, there's U1, which is present on the hemisphere, and it's easy, and it's always present in this after regularization. As for the P, it would be good to preserve it when possible, but I will say more on the next slide. And the Z2, it depends on the boundary conditions, because well, some boundary conditions break Z2. So what are the possible boundary conditions? Well, now the classical story in 3D Ising with the boundary is that you change spin-spin coupling along the surface, and then look at what happens as a function of this coupling of spins along the surface. And well, just like we adjust the bulk coupling to go from ordered to disordered phase in the bulk, we can also adjust the surface coupling to sort of have this ordered-disordered transition along the surface. And then there's this standard picture that you find in the literature is that there are 3 possible classes of boundary criticality. So the extraordinary one is when the Z2 is spontaneously broken along the boundary, and then it's even when you go sort of slightly to the left, where your bulk is ordered, the boundary, the bulk is slightly to the right, where the bulk is disordered, but the boundary still remains ordered. Then we have on the bottom we have the ordinary boundary condition, which has the opposite properties. That if we go to the right, where the bulk is disordered, but and the boundary is also disordered, and then in between them sits a special boundary condition. Now, extraordinary, as I said, they spontaneously break Z2 symmetry, so they actually can be thought of as a direct sum of what's known as normal and I guess the conjugate normal that corresponds to having how either all spins fixed to be pointing up or down. Of course, and it's been studied. There's lots of literature on this subject. I think there's these names, ordinary, extraordinary. They were I think they were coined in this paper by Binder in '83. But then there's a bunch of literature on the subject, including by people in the audience. Now, in this sort of fuzzy sphere approach, we would like to also, okay, here is there's a little review on the boundary spectrum. So in the case of extraordinary boundary conditions, there are no relevant deformations along the boundary, and the lowest scalar has dimension 3. It's the displacement operator, the normal component of the stress energy tensor as you move through the boundary. In the case of ordinary boundary conditions, which if you think in the mean field theory, they sort of correspond to Dirichlet boundary conditions on the order parameter in the bulk, there's one relevant operator along the boundary, and you can think of it as like you take the bulk order parameter to the boundary. In this mean field theory language, sort of, it's like it vanishes, so it obeys Dirichlet boundary conditions. But the coefficient of how it vanishes gives you this relevant boundary relevant operator sigma hat. And then in the special case, which in the mean field theory corresponds to Neumann boundary conditions, you have actually 2 relevant scalars along the boundary, which is like sigma and sigma squared. For sigma, there's an estimate of its dimension in the literature. I mean, in both ordinary and special case, there exists estimate from the bootstrap analysis, but in the special case, seems like there's no reliable estimate for the second.
Maybe from Monte Carlo?
So I couldn't.
I can give you a reference.
Yeah, well, I saw some references, but I couldn't like sort of extract the. Yeah.
It is?
It is a word, I think named 05 by Liu Qingdeng. We can talk later.
Okay.
Deng, Nightingale, and I forgot the third also.
But is that okay? Well, yeah, we can. And now we expect on the fuzzy sphere we want to have similar plots, but in sort of realize them at the quantum critical point, where we will be adjusting some coupling along the boundary to sort of go between these ordered and disordered phases along the boundary. So how exactly we'll do it? So one option is to actually work on the hemisphere, as I told you earlier, with some boundary interactions. Now, as I said, did I say it? Anyway, the hemisphere is going to break the particle-hole symmetry, because if you think of it as part of the full sphere, it corresponds to quarter filling. Like half-filled hemisphere is quarter-filled full sphere, and then you don't have particle-hole symmetry anymore. Another alternative is actually work on the full sphere, and then fix spins, freeze them in the hemisphere. Well, somehow in the paper I ended up freezing spins in the upper hemisphere and keeping the dynamical ones in the lower hemisphere.
What does it mean, freeze the spins in the lower hemisphere?
It means that you consider the subspace of a Hilbert space where they all point, let's say, up for explicitly breaking Z2 case, or all point to the right, which is like this.
Should I think that you're adding a big transverse field, a big longitudinal field?
Well, you can think, I guess, in this way too.
Which is a good thing, because it tells you that it's a local operation. And can you see that it's not exactly equivalent to the first type of, to just truncating the Hilbert field?
Well, I mean, it's a different operation, but like they both work. It's just like
the question: do they give exactly the same matrix that you diagonalize at the end of the day, or is it not quite the same?
Oh no, it's not exactly the same. No. So yeah, it's just like perhaps there's a more systematic way to address it, but I was just sort of looking at different ways and see which one gives better, less finite size effects.
Maybe I can comment that the second approach, I think, is also kind of ad hoc, right? So in principle, you could add a magnetic field on the or a transverse field on the upper hemisphere, but if you send it to infinity in a finite system, right, then the bottom hemisphere is also going to feel it very strongly, right? So you cannot send that strictly to infinity. And I think what your paper does, and Jean's paper, and Jean and Jan's paper does is they just by hand fix all the spins in the upper hemisphere to be either up or along the x direction. But again, I think that breaks locality.
I'm surprised, Max, that you're saying this. Because if the original Hamiltonian is local and that operation is performed, and if you, it just means that the original Hamiltonian somehow is not really local.
Sorry? I'm not complaining about the original Hamiltonian on the full sphere, and also if you just apply a finite magnetic field on the upper hemisphere, that's also perfectly local. I think the problem is when you just by hand freeze half of the orbitals to be either up or along.
Yeah, because the orbitals leak. They're not perfect, so they will leak into the upper hemisphere. If you did something local, it would shut down the bottom too.
But we don't have to do it by hand. We can just consider the limit. What happens with the orbitals if you take? Would we be okay with adding an extremely large magnetic field?
Well, it has to be. They have to take the infinite volume limit first, and then take the magnetic field large. Right?
Yeah.
Why?
Because if you take finite volume and h to infinity, then because the orbitals from the bottom hemisphere leak into the top hemisphere, they'll still feel this infinite magnetic field in the top hemisphere.
Yeah, but the leaking is like exponential so if you take the order correctly.
Okay, yeah, there has to be some sort. Yeah, it's some sort. Thank you. So there are many questions, but somehow we need to
yes.
We need to respect also the speaker, but also the coffee break. How much time do you think you need to get to We interrupted you a lot, so I apologize. But
yeah, well, I think I started like at 33 or 34, maybe.
That's already good, yeah. But
so it means that I have 5 minutes without extension.
Without extension, then maybe.
And I think I will fit into.
You're entitled to some extension.
But I think I will. Okay. All right. So the advantage of the second approach, though, is that the particle hole symmetry is preserved.
But one may still add some interactions along the equator to try to probe this transition between ordinary and special, or right. And what kind of interactions I will be adding? Well, perhaps I should have talked more to people, like people in the audience, and they would save me a lot of trouble. But in my approach, I was just looking at various different interactions that you can write and trying to see which ones work better. Like, for example, one option is to just take this V naught that is the spin-spin coupling in the bulk and just shift it by some value along the boundary. And also another is a transverse magnetic field at the boundary that only couples to the orbital that's closest to the boundary. Well, in fact, okay, here I give some various options of what could be considered, and what I did consider. Like, one is this magnetic field that only couples to the orbital that's closest to the boundary. Another option is to actually do something like this. That would, I guess, respect locality, but then then such magnetic field couples to all orbitals, but just still couples the strongest to the one next to the boundary. Both of these preserve Z2 and P. But, well, I somehow was using most of this one that doesn't respect locality because it's easier computationally. Because when you have to couple it to all orbitals, whatever, it takes longer to compute the matrix, the Hamiltonian. And for spin couplings, well, there are, again, different options. Basically, the one that I said that when you shift V naught by V, it actually corresponds to something like this. But so here, this one is the same coupling, but where all these factors are absorbed into the coefficient V in front of it. But such shift, where I shift V naught by V, it breaks again the particle hole symmetry. However, if I write something like this, then again the particle hole symmetry will be preserved on the full sphere. And there's another option, which again respects locality, is something like that, where I couple spin up to spin down, or NZ to NZ, just along the circle. But again, such interactions become computationally heavy, and it's harder to implement. But this one also respects all the symmetries. So the boundary order parameter that I'm looking at is actually just the spin of the orbital that's closest to the boundary. Which, again, people might have complaints about locality with this one. But I'm going to look at the behavior of the expectation value of this B, or B squared. So in the Z2 breaking cases, it makes sense to look at B, but in Z2 preserving case, B has 0 expectation value. It makes sense to look at B squared. And okay, as I said earlier, I'll be also shifting H by conserved charges to improve the answer, which might be related to the fact that I'm using various non-local steps. So some things that I don't do, though, it's like one could compute this various answers for different values of n and then extrapolate them. So, for example, the other paper by Zhou and Zhou do that. I don't do that, and also I don't use conformal perturbation theory to improve the answer, but that, of course, would be desirable to do.
Actually, in that they use conformal.
Yes, they do. Yeah.
But if the action is non-local, then conformal perturbation theory is a bit suspect.
But he's using a local action, I thought, because now he's
no,
because like LZ, right? The order parameter is non-local. The action, the Hamiltonian.
Oh, I guess I thought he introduced some non-local coupling, coupled to only one orbital.
Yes, yes. There's some non-local coupling. Plus when I cut as due to this extensive discussion, the cut or freezing the spins is also non-local.
Yeah, but he's not using.
But I'm not using the convolution.
Okay, that's fine.
but they are using. So I don't know. So then.
So then, yeah.
And then some of the standard steps that we do always shift the energy spectrum to start at 0, and then rescale the energy spectrum to ensure that the displacement operator has dimension exactly 3, which is the equivalent of the stress energy tensor having dimension 3 in the bulk case. So in the case of normal or Z2 breaking boundary conditions, so the best numerical results were achieved by using the full sphere with freezing the spins in a hemisphere, and then by also further adding. Oh yeah. So by the way, this is exactly what I mean by this. It means that I consider the subspace of the Hilbert space where they all point up, and then take Hamiltonian and violently project it to this subspace, because when you act with a Hamiltonian in this subspace, it takes you out of this. But this projection preserves all the symmetries nevertheless. So it's like this apparently non-local modification. And then I also add, some magnetic fields along the equator and perform the shifts to improve the answer. So the magnetic fields along the equator, you could, plot this expectation value of B as a function of the magnetic field and find some values of H where B is takes the maximal value closest to 1/2, because that's what's supposed to be in the broken phase. And somehow that value corresponds to the best result for the spectrum.
So how does the operator state correspondence work on this semi-skewed geometry?
Oh, it corresponds to half space, right? Where you
instead of slicing it with spheres, you slice it with hemispheres.
But again, you're going to diagonalize the Hamiltonian, and then once you extract the spectrum, how do you interpret the energy levels?
As the scaling dimensions of the boundary operators. Okay, I mean, I was a bit lazy. Instead of drawing plots, I just took a table from the paper. But anyways, there's one can identify some low-lying multiplets, such as the displacement operator and its descendants, or the next primary, the next scalar primary. But of course the finite size effects grow quickly as they go higher in dimension. For the ordinary, okay, in this case, actually somehow the results from the actual hemisphere or from this half-frozen hemisphere were somewhat similar in quality. And again, I tried different kinds of interactions, and so sort of the main working case that I present here is this hemisphere with spins frozen in the upper hemisphere. And there was this one extra step where I was scanning over the space of possible boundary couplings to sort of find the points where the spectrum looks more conformal. So you introduce some kind of cost function, for example, taking differences of energies between states that you suspect would be descendants of each other, and try to make them as close to integers as possible by scanning over the these possible couplings, the space of couplings. And again, it's possible to identify some low-lying operators and actually even find the dimension of this the relevant operator along the boundary, which agrees with seems to agree with the known numbers in the literature. Okay, there's some other possibilities which also give decent results, but only for this low-lying part of the spectrum. But I was sort of anticipating at least some of this discussion. I added this little note. I need to clean this mess up. And finally, special boundary condition, which is also C2 preserving. Here are only partial results, which is why I wrote it in brown color to sort of represent the unfortunate state of affairs. The results are only kind of very partial. The strategy was to vary the boundary couplings and identify the special phase transition, kind of like in the original paper. The approach that seemed to work the best here, but I mean only partially, is to shift the coupling along the boundary and use this boundary magnetic field and look at the behavior of the boundary order parameter. And we plotted. So the expectation is that such a quantity should be n independent at the conformal point, where the scaling dimension of this sigma hat, I take it from the bootstrap literature, and well, there's a certain plot which shows dependence on the spin-spin coupling and boundary magnetic field for different values of n, and n here is the number of orbitals on the full sphere. So on the hemisphere, there's half of them, and this and there's sort of a line where they intersect, but they don't intersect at exactly the same line. It's the intersection line is sort of moving with n, so clearly there's more work needs to be done. Like the spectrum has some features, some expected features, such that there's a vacuum, then there's the next one is the Z2 odd state, which is this sigma hat. Then you have Z2 even state, which is expected to be sigma hat squared. Then it's descendant and displacement operator. But then, like by using different interactions, like was able to
get the sigma squared. You said it's supposed to be relevant.
Yeah, it's supposed to be relevant. Yeah, exactly. So like I wasn't able to get a reliable estimate actually on sigma squared. So here more work needs to be done to have sort of a closer look at the boundary couplings. Perhaps actually, I don't know, maybe respecting locality in the best way possible would help. Anyways, let me summarize. So what I tried to talk about today. In the first part, it was basically just the story about the quantization by the lowest Landau level projection, how it's a powerful and rigorous alternative to other known techniques like geometric quantization or brain quantization, which I didn't talk about, but like people like it nowadays. And then there are these two versions where you either have a particle on M in the magnetic field or superparticle. And then I switched to studying the fuzzy sphere and fuzzy hemisphere and talked about using model on the fuzzy hemisphere and how it or on the half-frozen sphere and how it could be used to study the BCFT data. And in the extraordinary or normal boundary conditions, the answers were kind of okay, reasonable, then like good looking. In the ordinary case, it's still okay, but then there's like this, it was unclear there's indication that there's still room for improvement by choosing the best interactions, maybe respecting locality. And in the special boundary condition case, there are only some. I could see some features of the special boundary condition, but not able to get a reliable estimate for the dimension for the second. I mean, and actually get like this transition. Okay.
I suggest that we postpone questions to the break. Yeah. Thank you.